your data.
The only problem with that is we don't keep track of what the pictures are. I don't have enough time to determine. I only got to do that.
What? No, you only pick. You gotta stay above the
Scientists, engineers, and representatives from the Nuclear Regulatory Commission gathered this day at Cooper Nuclear Station to take part in the most critical moment in its new life, testing the core of this boiling water nuclear reactor. Of course, this was not the first nuclear reactor ever built, but this was ours. Some of us have studied 6, 8, 10 years to qualify for this responsibility. Many of us had our apprenticeship at other plants. But now, this is ours. The Nebraska Public Power District Cooper Nuclear Station. But in order to appreciate the importance of this moment, let's turn back over 6 years of time and look at some of the events which made this moment possible. The ice broke in the Missouri just a week ago. The year is 1968. The first warm breezes of spring are starting to come up from the south. Feasibility, economic, and environmental studies had been completed, necessary building permits obtained, and the stakes had been driven. Over 90 contractors will take part in this construction. And soon these two men will be joined by over 1,000 other workers. They began by digging a hole in the ground the size of the University football stadium at Lincoln. It was carefully separated into different stockpiles so that it could be replaced and used again. This was done to eliminate the sand and the silt that could not be dense enough to provide a strong foundation for the plant. Before beginning to build, care had to be taken to keep the excavation dry. A cofferdam and a cutoff wall were put in place to give extra protection from ground and river waters. Hard hats in life jackets began their struggle with the waters of the Missouri. The pump house, which will bring river water into the cooling system of the plant, will be built on the river bottom itself. To make this possible, a cofferdam was erected. The dam will be removed when the construction is finished. But for now, the water must be held back. To keep groundwater from seeping into the area, a cutoff wall was built of sheet steel piling completely encircling the excavation. It was driven into the ground, all the way down to bedrock, 60 and sometimes 70 feet into the earth. Even with the cofferdam and 4,000 tons of steel sheets in the cutoff wall, the water fought back, and the men continued their struggle. 27 deep wells were installed, pumping 3,000 gallons per minute back into the river. In spite of the extra care that was taken and the difficulties encountered, the final phase of site preparation was completed in only 9 months. The Cooper Station site was ready for another team of men. In the fall of '68, the initial work was started on the building structures themselves. A concrete foundation 10 feet thick, laced with reinforcing steel, was the first order of business. This will become the floor of the reactor building. What these men are creating is a foundation so solid, it will withstand even an earthquake. It becomes the base of the containment vessel, a structural steel safety device which will contain and hold the nuclear reactor pressure vessel. When it's finally in position, it will look something like a big brown light bulb with its neck pointed up to the sky. But before the containment vessel can take its place, there's a lot of work to be done. 100,000 cubic yards of concrete will be used here. There will be thousands of tons of steel and hundreds of miles of wire. But most of all, people. Workers from Nebraska, from Iowa, from Kansas and Missouri. Steel workers, cat drivers, pipe fitters and generator men from Colorado, New Mexico, Oklahoma, and California. Steam fitters, crane operators, electricians and carpenters, craftsmen, dreamers, builders. Safety is the major commitment in the design and construction of this plant. Testing quality control safety over and over again. From soil testing through even a sample of every batch of cement. Every valve, every switch, every wire. Testing, testing. The power plant uses nuclear energy to produce the same kind of electricity which is produced by the coal-fired plant. The difference is the source of heat. There is no significant difference in the steam that runs the turbine which drives the generator which produces electricity. In a nuclear power station, the heat for making steam is released by splitting atoms of uranium. In a sense, the station's reactor is a nuclear furnace. The uranium fuel within the reactor vessel is contained in bundles of fuel rods. When atoms of uranium are split or fissioned, heat is released. Atoms are minute building blocks of elements. They are so small that 36 billion could easily fit on the head of a pin. High-speed atomic particles called neutrons can split the large atoms of uranium and release more neutrons. If there is a sufficient amount of uranium present, the neutrons will hit and split other atoms. When this fission occurs, heat energy is released. Also, fission produces more neutron bullets, which can split more atoms, causing a chain reaction which produces heat continuously. Trillions upon trillions of atoms must be split to produce enough heat energy to turn the reactor's water into steam for the generation of electricity. While fission releases the heat energy, the uranium that has split atoms remains locked inside fuel rods. Control rods regulate fission to produce a constant level of heat energy. Control rod drives push the rods into the core of the fuel. As they are inserted, they stop the reaction. As they are withdrawn, the chain reaction spreads, producing more heat energy. In this way, the heat released from the splitting of the atoms brings the water inside the reactor to a boil, creating steam. After the steam turns the turbine generator, it's condensed back to water by the cooling of the river and returned to the reactor for reuse. The walls of the containment vessel are made of steel 7/8 inch in thickness. Below the vessel and out of sight is the torus containment. The torus is shaped like a donut and is located in the bottom of the reactor building. It's filled half full of water to condense any radioactive steam that might need to be contained. 1 million gallons of water is standing by. These safeguards of water, steel, and concrete won't rely on the operation of any complex equipment. Their physical presence alone will guarantee their function. When the reactor arrives, it will be contained in its own pressure vessel with walls 6 inches thick. And there is another safety barrier. Surrounding these multiple containment systems will be the entire reactor building. From Chattanooga, 1,300 miles by barge and towboat, down the Tennessee River, across the Ohio, and up the Mississippi and Missouri River to this spot, 3 miles south of Brownville, Nebraska. It was a long trip for the largest nuclear reactor pressure vessel to be shipped west of the Mississippi. The towboats guided the barge while hard hats and divers, boatmen and builders, wives and secretaries greeted the arrival. A slip was built especially for the barge. Once moored to the pilings, water from the river will be pumped into the barge and it will sink. The slip will be then filled so a vehicle can tie onto the skids and pull the reactor vessel to the raising site. The water will be pumped out of the barge and it will be used again. A light rain continued through the night and then began to let up toward early morning. This was it, the day of the lift. The nuclear reactor vessel would be gently raised nearly 100 feet into the air, moved across the top of the reactor building, and carefully lowered onto its base with precise accuracy. All of it more than 500 tons.
10-4, Paul, I'll have Ed give you the go. How about all Burns and Rowe personnel that's on the guys checking in?
Yes, I'm on my post.
Chuck Hall?
Everything okay?
Larry Trojan? Trojan here, and the representative from ACOG. It's moving, Paul. How is reading? Everything looks good down here.
5, 6, and 7, half inch to the east.
When she starts to travel to the east, that's when the strain is going to be on the guys.
Probably got about a 15-mile-an-hour wind up there now. Bill, we got a half-inch deflection to the east. That's all they're going to get. How's the nip back there, Larry Trojan? Just starting to overlap the dry well now. 10-4. Looks good. There was just a very, very slight trace of a tremor in the cable. Oh, let's go gauge. We got about 8 to 10 inches to go.
Successful lift.
The plant was now taking shape. In contrast to the huge reactor is the intricate wiring of the control room, the nerve center for the operation of the plant. Even a computer will be located in this room which will monitor the plant's operation. This turbine generator is similar in design to those used in conventional thermal plants. It will rotate at 1,800 revolutions per minute and generate 22,000 volts of electrical energy. This power will be transmitted to help serve more than 300 cities, towns, and villages, as well as other utilities, not to mention the countless number of farms throughout the district's service area. The fuel has arrived and the vessel is ready. The fuel is in the form of uranium oxide, which has been pressed into small pellets. Each individual pellet will produce the same amount of electricity as 1 ton of coal. In this initial fuel loading, there will be more than 3 million uranium oxide pellets placed in the reactor. The pellets are contained in fuel rods, which are bound together in bundles. To load the fuel, the bundles must be lowered into the reactor's core. As each bundle of fuel is lowered into place, the control room charts it, and the control panel acknowledges its position. For all 548 fuel bundles, this initial loading will last for approximately 18 months. This nuclear energy will equal the burning of 3.5 million tons of coal, or 10 million barrels of oil each year.
Less than 1 ppm. Less than 0.1.
The turbine and generator are undergoing their final set of tests. So heavy is the generator's core that it must be kept turning slowly, even when it's not operating, so as not to bend its huge shaft. The turbine and generator checked out. The fuel has been placed in the reactor. Every component is fitting together perfectly. One last component has yet to be lowered into the reactor. Its job is simple but important. Its task is to prevent minute droplets of water in the steam from going into the turbine, allowing only hot, dry, efficient steam to enter. Hot steam is a dry gas. This component is simply called the steam dryer. Finally, it was time to put the reactor vessel head in place. A large tubular gasket of silver was secured under the head before it was lowered over the reactor vessel. The team of men worked on into the night, and by morning the head was secure in place. After the years of time-consuming construction, progress now seemed to be moving more swiftly. And that brings us back to the afternoon of February 21, 1974. The construction was now completed, and the first self-sustaining chain reaction in the nuclear reactor was taking place. Under the watchful eyes of the representatives from the Nuclear Regulatory Commission, the operating personnel from the Nebraska Public Power District will take this finely tuned $400 million facility through its paces to test the vital core of the reactor. Only if it meets this critical examination will the key to its future be turned, and the 800,000 kilowatt Cooper station will soon be on the line. Though much of the technology of nuclear power stations is similar to a conventional fossil fuel plant, the source of heat is obviously not. A new generation of nuclear scientists and technicians is required to work on this new technology. This entire wing of the Cooper plant is devoted to radiation waste control. Every nuclear power plant produces a small amount of radioactive fission products during the routine operation. Most of it remains in the fuel elements and is returned to the manufacturers as spent fuel for reprocessing. However, all other forms of contamination are disposed of with the highest degree of concern and the most advanced technology. For example, fission product gases produced in the reactor are treated by first removing the non-radioactive gas of hydrogen and oxygen. Virtually all the remaining gases are trapped and stored throughout the life of the radioactive decay time, in this case, 40 days. No radioactive waste byproducts are overlooked. All water, even from floor drains in the plant laundry, is pumped into storage tanks, tested and released only if no harmful contaminants are found. The most sophisticated scientific equipment is used for this search. If the solution should be found contaminated, the contaminants will be removed by filtering or condensing them into a small volume and disposing of them by shipping to radiation burial sites. Even air and water around the station are regularly monitored as another safeguard, not only by the technicians of Nebraska Public Power District, but also by an agency of the state of Nebraska and the Nuclear Regulatory Commission. After there was complete assurance that Cooper Nuclear Station would perform safely and that all standards for protection of the environment would be observed, the commercial operation began. From the quiet of the control room, every function of the plant is monitored. The reactor is quietly synchronized with the rest of Nebraska Public Power District's network of 7,000 miles of high-voltage transmission lines. Miles up the Missouri, in the historic town of Brownville, you can still buy stone-ground wheat or a hand-turned pot. And in the summer, during festival time, the whine of a country fiddle is heard over the feet of dancers in the street. It looks like little has changed in the last century, but it's well known that our need for power has multiplied many times. We can no longer solve new problems with old answers. To meet the challenge of the growing use of electrical energy, even with the hope of moderating its growth through conservation, is still a critical problem. Energy is still the key to man's greatest goals, his dreams for a better world. This, then, is our commitment to meet the challenge.